Hello, my name is Roni Shouval. I'm an assistant attending on the adult bone marrow transplant service and cellular therapy service at Memorial Sloan Kettering. And I would like to thank Professor Motti, Professor Nagler for inviting me today to speak about machine learning and artificial intelligence in hematology. I'm going to start with this painting entitled Edmond Deboami. Aside from it being a really nice work of art, what's special about it is that it was generated by an artificial intelligence or AI algorithm. If you look at the lower hand side, right hand side of the painting, you'll find that the signature is a formula which is taken from the algorithm code. And the painting is named after the developer of the algorithm, Ian Goodfellow. Seeing this makes you wonder, right? We have now AI algorithms that can paint, drive, even see, quote unquote. And it seems like in medicine, we may be lagging behind a bit. So in this talk, I'm going to share with you some general concepts of machine learning and artificial intelligence to kind of introduce you to the field and touch on some applications in hematology. Here are my disclosures. Sorry. Some refer to the current period in mankind's history as the data era. And this is because every activity we do these days generate a digital signature. This also holds true for medicine, right? Where we have the clinical notes, pathologies, labs, radiology all goes into the EMR and has sort of a digital footprint. Now, more recently, also genomic data is part of the patient care, and this really generates huge amounts of data. Just as an example, I'll show you this renowned figure from the NIH, where we see the drop in sequencing costs for the whole genome sequencing over the past 2 decades, and the decrease in cost, where now we're talking about $1,000 or even $100 per genome, exceeds a reduction of the cost in computational power, as predicted by the Moore law. And this generates huge amounts of data. But we also need technology to process this data in order to get some meaningful insights, because we are obviously limited by our biases and ability to perceive these large amounts of data. This also holds true, obviously, for clinical data and the different sources we have there. And this sort of data, it generates a lot of investments because people want to capitalize on these data. However, our focus would be on this talk would be on the technology, mainly machine learning and artificial intelligence technology used to process these large amounts of data. So machine learning was originally defined, I would say, by Arthur Samuel, who is one of the fathers of gaming, video games actually, as a field of study that gives a computer the ability to learn without being programmed. What Samuel did was design or program a checkers playing program that could play tens of thousands of games against itself, learning which position led to wins and which to losses. And as it played more and more game, it gained more experience and became a better player than Samuel itself. So it improved with experience and was not implicitly programmed to capture all moves, but rather it learned what are the best moves. Now, this is sort of a rather old definition, I would say, of machine learning. The more sort of contemporary approach is looking at machine learning as a continuum, where we call it the machine learning spectrum, where on the lower side of the spectrum, we have fully human-guided models or machines, while in the higher side of the spectrum, we have fully machine-guided models. And I'll show you an example. For instance, let's take the CHA2DS2-VASc score, right, where this was developed by investigators, selecting which variables they thought are predictive of cardioembolic events in patients with atrial fibrillation. So there is a lot of human decision in deciding which variables would go into the model, for instance, CHF, age, and others, and then also how to categorize variables, age above 65, below 65, etc. So that's sort of the lower hand side of, because there is a lot of human intervention in this decision or this modeling. On the higher end side of the spectrum, we have face recognition algorithms, such as those used in a Facebook, Apple, Google, etc., where the algorithm actually takes raw data as is, very complicated, very heavy files, and just feeds off it directly with minimal human intervention in the middle. Now, these could be very accurate models, but the trade-off here is that they're data hungry, requiring a lot of samples for training. Overall, most machine learning algorithms fall somewhere in the middle of the machine learning spectrum. Now, machine learning is part of artificial intelligence, and this is obviously a joke showing the Terminator 2 Judgment Day poster, but because this is based on, these are machines based on artificial intelligence, so we're definitely not there yet. But thinking about how we perceive artificial intelligence and what's the definition, well, it's broadly defined as the ability of a machine to accomplish tasks typically associated with intelligent human behavior, such as problem solving or learning. Now, contemporary notions of artificial intelligence are more task-oriented than what was previously thought as defined as artificial intelligence. And obviously, artificial intelligence is based on machine learning. Now, machine learning and artificial intelligence is all around us these days, whether we search the web, use recommendation systems such as in Amazon or Netflix, autonomic driving, and many other applications. And it's gradually entering medicine as well. What are the applications of machine learning? Well, in oncology and hematology, the main categories would probably be diagnosis. So we could take, for instance, slides or images and categorize the diagnosis based on these images from the slides, classifying what is a likelihood diagnosis. It could be used for prognosis, risk stratification, prediction of the expected outcome of specific patients. It could also be used for designing intelligent treatments or therapies, such as designing antibodies or other drugs. So there are a lot of applications, and I think it would have, it does already have great utility. When thinking of machine learning, we could broadly classify it into two types of learning: supervised learning and unsupervised learning. There is also reinforcement learning, which I won't touch in this presentation. So let's go over briefly on these types of learning. The first type is supervised learning. And in supervised learning, the goal is prediction of an outcome or a diagnosis usually. A model is trained on a data set that includes features, which are the terminology for variables in machine learning, and labels, which includes the outcome or class of interests. The algorithm generates a function which maps the features, the variable, to the outcome, to the label. So, and then use what it learns to predict the labels or the outcome on new, never before seen data. So, for instance, if our objective was to predict short-term mortality following allogeneic hematopoietic cell transplantation, as seen in this acute leukemia working party study, the model was trained on a data set containing information about patient, disease, and transplantation characteristics. as well as the associated outcome for each individual. So we learn from what variables are linked to the outcome and generate this decision tree model. Now, when encountered with never before seen patients, the model just runs the patients through this tree and generates a prediction. Now, generally, the performance of supervised learning model is judged by their accuracy in predicting outcomes across one or more sets of data that are not included in the development process. The other type of learning that we typically see is unsupervised learning. And here, it's not about predicting the outcome or the label. It's more about finding patterns in the data. So we don't use the labels of the data to learn, but rather search for patterns in it. And the most common type of unsupervised learning method is probably clustering, which groups data into similar subgroups. And I'll show you here one example by Lacey et al., who identify molecular subtypes of diffuse large B-cell lymphoma based on unsupervised learning method on specific gene genomic alterations. Now, the algorithm identified 5 subgroups based on a large targeted gene sequencing panel. Now, here you can see the different groups that were kind of clustered together. And right, there is no hard truth here. This is sort of artificial since the algorithm identifies the different groups according to their similarities. What we typically do when we have the unsupervised learning or clusters generated by the unsupervised learning, we look at the association between these clusters or groups and certain outcomes. Here you can see how the different groups are associated with distinct overall survival trajectories. So this comes to show you how you can use unsupervised learning in research in hematology, essentially, and other forms of research as well. It is important to note that the process of developing and validating and evaluating machine learning algorithms is very similar to the one used in traditional statistical approaches. And this statement, we'll call the tripod statement, really sets the stage and explains how a model should be developed and validated. There is now a version that will hopefully be published soon specifically for machine learning. But again, it's very similar overall. Data mining is an approach that seeks to discover knowledge in databases in an automatic or semi-automatic way or process. And machine learning are tools in data mining. So they serve the goals of data mining. And there are different standards, such as a CRISP-DM described here, for performing data mining studies. And to be honest, they're very similar to what we saw in the tripod statement. It follows 6 stages, starting from understanding the problem and data, preparing the data, modeling the data, evaluating it, and then deploying it. In the next few slides, I'm going to go with you on the different stages. So the first stage is understanding the problem. While there is a sort of common misassumption, I would say, about machine learning and artificial intelligence, that you can just throw in the data and not really think about it. And this is not the case, because the first stage of of developing machine learning algorithms is actually having some sort of hypothesis or a specific aim in mind. You can't just throw it and without any thought. We want to have value in the model. We want to have some assumptions behind it. You also need to decide what sort of learning type are you interested in. Are you interested in sort of supervised learning project versus unsupervised learning project? you need to understand what are the available data sources out there. And we'll touch about on it a bit later, but some prediction tasks really require a lot of data, and a lot of times you would need external data to validate. And another point is personnel. Now, for machine learning studies, you kind of need people with a special set of capabilities, which are found more and more these days because machine learning is taught in many statistics courses, and hopefully medical students will be exposed more and more to these sort of methodologies. But still, it can be challenging to find personnel that would be able to perform these type of studies. The next stage is understanding the data. So obviously you need to obtain the data, and then you need to describe the data, understand the descriptive statistics as you would do in any statistical project. It's helpful to visualize the data and do exploratory data analysis. And you also need to be cognizant of the biases in the data. Let's say the data we want to predict outcome of patients with AML in undergoing allogeneic transplant. So obviously, if you take a transplant registry, you won't have arms or patients that did not receive transplant, and obviously there is selection bias in patients going to transplant, and you always need to keep that in the back of your mind. The next stage, which is probably the most time-consuming, is preparing the data. So you need to find a strategy to cope with missing values, whether to impute them or exclude them. There are benefits and shortcomings for each for each decision. A lot of times the data is high dimensional, meaning you have many more variables than the actual number of cases. This is called high dimensional data. And there are methods for feature selection, reducing the number of covariates in the model to include only the most informative ones. And this really depends on the algorithms that you're using. Some algorithms are more permissive for large data, others are not. So it's on I say model-to-model basis. You may need to feature engineer the data, meaning transform some of the features, let's say log transformation, or change it to dummy coding. So it really depends on the algorithms. And you would want to split the data into training and testing at this point, and I'll touch on this in the next slide. So next stage is modeling. But before building the model, we must establish a mechanism to test the model accuracy and generalizability. This is imperative in order to avoid overfitting, which is a frequent hazard of machine learning algorithms because these are data-driven. They're learning from data. And you can see here on the curves on the left, overfitting means that your model performs well on the training set. So the model could be very very complex models that really manages to predict the outcome of every patient on the training set. It learned from the data. But then when you present the data to a testing set, an independent data set, then the prediction error, where you see here on the y-axis, goes up because the data is overfitted. Your model is overfitting the data on the training set. That's why it's important to have some sort of testing mechanism. Now, in data-rich scenarios, the best solution would probably to divide the data into a derivation set or training or development sets. These are similar terms, and a validation set. A training set is used to fit the different models, tune their parameters, and this requires often multiple adjustment. The validation set is used for estimating the prediction error for the final model. The model was selected on the training set. Ideally, you would have another independent data set, which is a testing set, which is completely external. But in reality, a lot of time we don't have enough of data to create these type of data set, and we may use only training and validation without a testing set, or just use a sort of internal validation sets. Once you established your mechanisms for training and testing, you actually start developing the models on the training set. And there are numerous algorithms, machine learning algorithms, that you could use to train the data, whether it's, I list here a few examples: random forests, artificial neural networks, support vector machines, logistic regression, and each have their sort of benefits and drawbacks. And it kind of depends on what you want to predict or learn. You also need to be aware that these algorithms do not deal with time to event data, typically do not deal with time to event data, meaning they do not account for sensor data or time to event data such as overall survival, progression-free survival. But there are machine learning algorithms that are designed to predict these sort of events. And once you train the different data, evaluate them, whether internally, and this is many times used with sort of sampling techniques such as cross-validation and bootstrapping, or externally on an external data set, you need to evaluate the data, and that's the next stage. And there are different metrics to evaluate the models, and there are different metrics to evaluate the models, whether it's the discrimination or area under the curve, C-statistics. These are all similar terms, and these basically evaluate the ability of a model to distinguish between patients or cases that experience or did not experience the outcome or diagnosis, meaning that the ability to assign a higher likelihood to a patient or a case that experienced the event versus one that did not experience an event. This measure ranges from 0.5, which means a model that is not better than chance, to 1, which is a perfect model. Another important measure is calibration, which reflects the agreement between the observed endpoint and the prediction. So, for example, if you predict a 10% risk that a patient will die with 1 year, the observed outcome in the test set should approximate 10 deaths per 100 patients. And a lot of times we assess calibration graphically, as seen here in the calibration plot. Other metrics to evaluate models are based on their interpretability. Some machine learning models are black box models, which you don't understand the rationale behind, while other you can explore what were the drivers of the prediction. And then the last axis you could evaluate models is compare it to human expert recommendation. So seeing the different metrics, comparing them between humans and the machine. The last stage of developing a model is the deployment. Once a model has been built and validated, we want to release it for implementation. And optimally, the model will be integrated into the clinical workflow with an ongoing effort to assess its effectiveness. This is, for instance, a model that Joshua Fine developed for outcome of patients that are going haplotransplants from the EBMT. And you can see here's a website he built that you can actually enter the patient features here on the left-hand side, and then you get a sort of prediction which you can calculate on a website. So this is a deployment of the model. Now, going to hematology, there are numerous examples these days of studies using machine learning algorithms for either outcome prediction, but we also see a lot of activity for diagnosis of a certain malignancies or conditioning or conditions. And I'll share with you a few examples. This is an interesting study where the group took CLL patients that were prospectively collected and trained a model over 4,000 patients to predict infections in CLL. And in CLL patients, it takes a large number of covariates, laboratory disease, patient features, and predicts the risk. And the prediction is used. The prediction model is actually an ensemble model, meaning it harmonizes or just integrates the average prediction across different algorithms. And based on the prediction, patients are actually assigned into an intervention. So this is, for instance, an outcome prediction algorithm. Another interesting study predicts the likelihood diagnosis of patients based on laboratory data and clinical data. So, and gives the actual certainty of the diagnosis. And you can imagine these sort of algorithms integrated into the EMR, providing a diagnosis based on what's available, the clinical data available. One of the fields that is really exploding is a use of deep learning algorithms for a computer vision, or to deduce conclusions from computer vision. And an example recently published in Blood shows how images from cells from the bone marrow can predict what is a cell type. And the way that this algorithm or model was developed, it learned from raw images the assignment of certain cell types. And this was done using a deep learning algorithm called convolutional neural networks, which imitates human learning, essentially. So the cells were annotated by pathologists. The algorithm learned the different classification and annotation, and then could identify accurately what cell types exist in a completely new slide. And this, I believe, is going to transform hemopathology in the next years, because you can imagine identifying not only normal cells, but also pathological cells. And we know that some of the hematological diagnoses are really hard to make. And I think these tools will help us make decisions and diagnoses. So there are a lot of challenges in artificial intelligence and machine learning, and I'm just going to list a few of them. The first is we need a lot of data. A lot of these algorithms are data hungry, and when you use single center data or siloed data, you really limit the ability of your model to maximize the potential from data. And obviously, you're exposed to less samples, so this affects also the generalizability, which is or reproducibility, which is the next limitation. A lot of these algorithms, to actually see whether their utility, we need to test them on external data set and to see if they're reproducible. And this is another challenge, because we know how hard is it to share data across centers, across agencies. And I think collaboration is the main mean to actually overcome these two barriers. The third limitation I would like to mention is interpretability, where a lot of these algorithms are black box algorithms. We don't understand the rationale behind the prediction. As clinicians, we really want to understand what's going on why a certain prediction is made. Maybe we could also, maybe this is a modifiable factor. So if we understand what drives a prediction, maybe we could fix it and improve the patient outcome. But there are ways today to explore models, and this is a field that has shown a lot of progress in the past few years. The last point is, or challenge, is a regulatory challenge. That the FDA actually have guidelines these days how to evaluate artificial intelligence algorithms, because this is sort of a device and you need to test the utility, generalizability. And this is very important, especially when thinking on how these models are prone to overfitting. So a lot of effort is invested in the regulatory aspects of machine learning and artificial intelligence models. I listed here some key questions I believe one should ask himself or herself when developing machine learning algorithms or models. So the first question is, how complex is a prediction task? I mean, if it's something very straightforward and you don't need a lot of data, maybe machine learning is not the best solution. I think if you have a simple and effective solution, it may be preferable to these sort of complicated machine learning algorithms that you don't necessarily understand the rationale behind the prediction. The second question is whether you want the prediction to be based on measures that the clinician could just enter on the bedside. Let's say you have 5 parameters that you would like to calculate the risk of a certain patient, versus whether it would actually need a computer to ingest a very large amount of data, and this could only be done, in an EMR system that it takes into account all data available. And these sort of simple tasks where you don't need a lot of data, again, may favor a more simplistic modeling approach. Another point you need to consider is how many samples exist to train and test the model, because we know that sort of complicated prediction tasks really require a large amount of data, and these algorithms are data hungry. So you must make sure you have enough samples to train the model, and this is empiric. It's hard to anticipate a priori how many samples you need. And the last point is whether you want the model to be interpretable or not, and do you want to understand the rationale behind prediction? And as I alluded to earlier, that may not be the case in some machine learning algorithms. Thinking about the future, one interesting approach for machine learning and artificial intelligence is taking not only one modality, what we call unimodal models, but integrating different modalities, multimodal models, to predict the outcome. So harmonizing or reconciling clinical, radiological, genomic, pathological data all into one multimodal machine learning model that would predict the outcome. And improvements or advanced progress in technology, storage, cloud processing, etc., really is going to drive this field forward. And there are several examples published to date using these multimodal learning techniques. So in summary, machine learning are increasingly being used in medicine. And I try to present here sort of a standard framework for model development and validation, which is key for introducing and including machine learning algorithm in clinical research and to actually affect patient care. We touched on concepts such as interpretability, accessibility to data, reproducibility, and generalizability, and these should guide model appraisal. Finally, I want to stress that the clinical aim and not the technology should guide the modeling technique. So it's not about the technique or the machine learning algorithm. It's actually about what data is available what's a prediction task, and sometimes a simple solution is a better solution. With that, I'd like to end and thank especially Joshua Fine, who helped a lot on these projects, Professor Motti, Professor Perales, Professor Vandenbrink, Professor Nagler from Shiva, and my different funders. Thank you very much.